remembering to start recording at the beginning.
I looked at the video and the sound and the board looked great.
Oh, okay, good.
Easily hear and read everything.
Okay, well, that's really good. All right, now, today's class might be a little difficult just because normally I seem to be able to get through about 4 or so pages of notes in one class period, but I have 9 pages of notes here on the LED decomposition. And those of you who took 561 have seen this, but that is not everybody. So I may have to abbreviate some things. So I'm just gonna go ahead and maybe not to pay too much attention to the notes themselves and just do whatever it takes to write LU, and we'll see what happens. Okay, so. So first to motivate today's content. So the process that we established from last time, solving general system Ax equals B, where A is where an invertible is pretty much what's done in an intro linear algebra class. So the idea is so from your original problem, you transform it into an equivalent problem where the matrix U is, no, I keep doing this wrong. What's wrong? I'm just off in general, it seems. Upper triangular. Use an upper triangular matrix. And the way that is done is through row operations. Applied to both A and B. And the row operations have a form, row I is equal to itself, where row I is overwritten with itself minus the multiplier Mij times rho j. So that operation is repeated for I greater than j. So to eliminate all entries that are in the lower triangle. So based on the entries of A, we have a formula for a multiplier. Mij is equal to Aij over Ajj. And for now, we're just assuming it's non-zero. And we start with first column, j equal 1, and then keep going to the right until all the columns are processed. We fit in that, so the actual operation, row operation, is figured out based on the entries of A. We apply it to A, and then we also apply it to B. And that's first step, and then the second and final step is we use back substitution. Apply to this new upper triangular system, and then we have our solution and we're done. Okay, fine. It gets the job done. But here's the problem. What we need to solve Ax equals B with A but different B. Because if we do that, we don't want to repeat this whole process. There's no reason to apply the same row operations to A every time we get a new B. That's repetitive because the upper triangular matrix U has nothing to do with B. It's going to be the same upper triangular matrix every time. But we need some way, if we apply row operations to A and B once, and we get a different B, we want to apply that same sequence of row operations to the new B. So for that, we need something that we currently don't have. We need some kind of record or storage of the row operations. Okay. All right. So what I'm going to do today is we're going to take a closer look at how Gaussian elimination, this stage here, how that works to, so we're gonna look at this whole solution process in a different way to be able to repeat the solution process on a different beat. Now, we just call it Gaussian elimination because Gauss gave the world a lot of mathematics. He did not give us Gaussian elimination. Gaussian elimination has been carried out thousands of years ago by the Chinese. There are records of that. So how his name got attached to it, I should remember because I did see like a talk about this, about the history, but fortunately I'm not remembering, but it happens. And I'd love to have something accidentally named after me. Okay. All right. Now, before I get into that, though, I want to give you an example of this kind of situation, how it actually comes up. Because right now it seems like, oh, well, who would ever need to do that? That's just a made up situation. But actually, it's not. I think this is not in the notes, so it's going to make it even harder to cover those 9 pages, but whatever. Suppose we have a system of ordinary differential equations, ODEs. So y prime is equal to by for some matrix B. So then you can solve numerically by, there are many types-stepping methods, but I'll introduce an implicit one called backward Euler's method, also known as implicit Euler. And that method would be yn plus 1 is equal to yn plus delta t b times yn plus 1, where yn is approximation of a solution y at time tn, and tn is equal to n times the time step delta t. Okay. Oh, yeah. All right. Now, if I rearrange this vector equation, I get the following: identity minus, so I'm going to take this last term here, move it to the other side, and factor out the vector yn plus 1 to the right. So now we have this, and this is an AX equals B problem. This is the A, this is the X, and this is the B. So time stepping to compute solution y of t, this approximation of it, would require solving many systems of equations for, because this happens for n equals 0, 1, 2, so on. Same matrix, different right-hand side. So it is a real thing. Okay. Now, okay. So now let's take a look, a closer look at the row operations that are performed from a point of view of matrix multiplication. And this is often helpful, like whatever operations you're performing, if you can describe it in terms of larger entities as a operation involving matrices, matrix multiplication, for instance. It gives you a perspective on things that can help you better understand the algorithm as a whole and maybe even improve it. Whereas if you're working exclusively at the element level, like the IJ level, it can be hard to see, but you miss the forest from the trees. So we're going to look at the forest. Okay. Actually, Nemo, maybe a good idea if you were to take a picture of a board and then, yeah. It's probably time to write that to class we have over to. Yes, I'm exaggerating. Okay. This is all fluff anyway. I guess it's kind of sort of relevant to your thesis, so. Yeah. Okay, so, so any of you, the three row operations I described last time, scaling a row, swapping rows, or subtracting a multiple of a row from another row, can be described through matrix multiplication by elementary row matrices. So the row operation that we care about, row I, is overwritten with itself minus multiplier times row J. It's equivalent to the following, where you take your matrix A and you multiply it on the left by a matrix that is identity, except for one thing, that's in column J and row I, we have a single non-zero element minus Mij. So multiplying this matrix on the left, so multiplying A by this matrix on the left will keep all the rows the same, plus the ones here along the diagonal, that's identity matrix, except it's going to take because it sits in the Jth column, it's going to have the effect of multiplying row J by minus Mij and adding that to row I. So because it essentially sits in row I, it's going to work on row I. And because it's also sitting in column J, it's going to take this combination of row J, subtract from row I in A. Okay. So that's just one row operation. They eliminate a single subdiagonal entry. Now, let's extend that to eliminating all the entries that we need to in a single column. All the entries that are below the diagonal. So what you're doing in that case is that's equivalent to multiplying your matrix on the left by a matrix that is all ones down a diagonal, all zeros up here. And then in column J, you'll have all the multipliers negated. So starting from row J plus 1 all the way down to the last row, row N. Now, actually going to fill in more of the ones. Okay. To give you a better idea as to why this works the way it does. Because what are you doing when you carry out matrix multiplication? You're taking entries across a row of the left matrix and entries down a column of the right matrix, and you're multiplying corresponding entries, and then you add all that up, and that gives you an entry in the product. So what happens in this case, as I go across a particular row, like in this case, row J plus 1, I'm going across this row and down each column of A. And when I get to column J here, then I'm dealing with row J in A, and I'm multiplying an entry by this. Then I keep going across the row and I come to this 1. That's being multiplied by the entry in row I, where I is greater than J. So I'm just taking an entry by itself. And then, so then the entry in row I has this times the entry in row J subtracted from it, which is the exact row operation. And really what's happening is when I'm working on column J, what I'm doing is first I'm multiplying by one of these matrices where I is J plus 1. Then I'm multiplying by another where I is J plus 2. And I keep multiplying by matrices of this form. So this matrix is the product of all of these matrices for I equals J plus 1 all the way down to row N. It's just that because this matrix is almost identity, except for this one non-zero entry here, multiplying all those together works out very nicely, very simply, and gives us this. So that's all it does. It just stacks the negated multipliers in column J. Okay. Any questions so far? All right. I'm going to give this matrix a name. I'm going to call it MJ, with a superscript J is in parentheses. All right. So this admittedly oversimplified Gaussian eliminated process, where we're not having to worry about row interchanges, and I'll talk about that later, can be described as this matrix product, where I start with A and I multiply it by this matrix with J equal 1 to eliminate all the subdiagonal entries in the first column. And then I repeat that for second column, third column, and so on, all the way to column N minus 1. It's the last column I need to do anything in. And the result of that is my upper triangular matrix U. And those same row operations are applied to B. So I have M1, 2, and so on, up to M minus 1, and that gives us my modified vector Y. So now then it would solve system UX is equal to Y. Now, so far, in our very limited time in this class, we've already learned about certain categories of matrices, matrices that have a certain structure. What type of matrix is this one? It is lower triangular. But there's something more we can say about it. All the diagonal entries are equal to 1. So each MJ is what's called unit lower triangular. So a unit stems from all the diagonal entries equal to 1. Okay. I see my shorthand for upper and lower triangular. I keep using the one for lower triangular when I mean upper triangular. So I have a shorthand for this too. So my symbol for unit lower triangular is lower triangle, and I'm gonna put a 1 here. So because I don't like to write out, I don't even like to write out lower triangular, let alone unit lower triangular. All right. Okay. Some nice properties that unit lower triangular matrices have is the following. These will be quite helpful to us. Okay. First, if you have a unit lower triangular matrix times another unit lower triangular matrix, the product is a unit lower triangular matrix. In general, multiplying matrices preserves triangularity. Lower times lower is lower, upper times upper is upper. Unit times unit equals unit when it's already triangular. I think about this, matrices kind of look like shark fins. Never thought of that before, and how many years I've been teaching this class, but yeah, and now I can't unsee that. And also, the inverse of a unit shark is another unit shark. Okay. Unit lower triangular inverted is unit lower triangular. Now, so what about these matrices M sup J? It turns out their inverses are very easy to get. So if MJ is a matrix that has all ones down diagonal and then these negated multipliers sitting in column J, and I won't show you how we get this, it's something that could be verified if you have a lot of time on your hands. But the inverse of MJ. So first, because MJ is unit lower triangular, the inverse is also unit lower triangular. So what's happening in the lower triangle? It turns out we have almost exactly the same thing. It's the multipliers again, only without the minus sign. It's the multipliers themselves. Okay. Okay, so then what I can do, if I return to this equation and multiply both sides on the left by these inverses, starting with mn minus 1 inverse to cancel this one, and then going backwards. So multiplying by them in reverse order on the left. Until I'm left with only A on the left side, I get the following. So A is going to be equal to, so I'll put U right here. And the first matrix that I multiply by both sides on the left is M n minus 1 inverse, then M n minus 2 inverse, and so on, until I get to M2 inverse, then M1 inverse. Now, if I label these, I'm calling them MJ inverse, but the reduced clutter, I'll call it L sup J. So that's the same thing as saying that A is equal to L1, L2, L n minus 1. Now, the M's are unit lower triangular, therefore their inverses are unit lower triangular. So these are unit lower triangular. Therefore, their product is unit lower triangular. So all of these multiplied together, I'm going to call that L. U. So what we have is a factorization of A. So this is called the LU factorization, also known as the LU decomposition. So L is unit lower triangular, and U is upper triangular. So Gaussian elimination amounts to the factorization of A into these triangular matrices, provided that we do not need to interchange rows during the process due to the danger of dividing by 0. That will be accounted for a little later. So not every invertible matrix has an LU factorization. So I'll address questions of the existence of uniqueness a little bit. But are there any questions up to this point as to how the factorization was arrived at? Okay. There's two things to deal with. One is we know what each of these individual L's look like. What does a product, does plain old L look like? And then, aside from that, what does this mean for the process of solving AX equals B? How does having LU decomposition impact that? Especially for a situation described at the outset, where we want to be able to solve system efficient, several systems efficiently with the same A but different B's. Well, it turns out that the matrix L is very easy to describe. So it's unit lower triangular. And the lower triangle is filled with multipliers. Each multiplier, Mij, stored in the entry Ij that's used to eliminate. So it's quite convenient. Now I'm going to look at the solution process. First, you perform LU decomposition, you factor A into L and U, and that is just Gaussian elimination. And the U is the same matrix U that we've been getting through rows of row operations. That part's no different. What is different is as we compute multipliers, we store them in the lower triangle. So you start so everything can be done storage-wise within just one matrix. Initially, you have your matrix A, you perform row operations on it. The upper triangle is transformed operation by operation into U. As you get a multiplier and perform a row operation, you stop Mij in this position in the lower triangle. So the entire matrix is used. So the upper triangle and the main diagonal hold U. Everything below the main diagonal stores the multipliers. We don't need to store the diagonal of L because we know what it is. It's all once. So we don't need any additional storage for the LU decomposition. But once we have L and U, then what do we do? Well, for AX equals B, that's equivalent to LUX is equal to B. Just because we're replacing A by LU. So if I take this vector U times X, which is currently unknown, and I call it Y, then that means we have a system of equations. Ly is equal to B. And we can solve by forward substitution. Yes, I'm being lazy. Now I write these things, but now L is a unit lower triangular matrix, so that process takes over n squared operations. It's just the opposite of what I showed you last time with back substitution. Now, this step is equivalent to what we were doing before in the original version of Gaussian elimination, where we apply row operations to A and then we apply the same row operations to B. So really, the whole process of Gaussian elimination to apply to both A and B is you're multiplying on the left by L inverse. So it's mathematically equivalent to that. Once we have Y, we have this relationship UX is equal to Y. So now we solve max. Using back substitution. And then we're done. As far as the computational expense, so this takes 2/3 n cubed operations plus additional lower order terms. So that's the most expensive part. For substitution takes n squared minus n operations. And then forward back substitution takes exactly n squared. The reason for the difference in the two is L is unit lower triangular. So we don't need to divide by diagonal entries because they're all equal to 1. And most important, after we solve Ax equals B, if now we need to solve Ax equals B for a different B, we don't have to do the first step. So the most expensive step only has to be carried out once. And then with a new B, we'll just solve, we have L, so we just use that in the forward substitution and then the back substitution. All right, questions about any of that? Should mention that on the second page of the notes, I have an example of like a 4x4 matrix A, where I actually show what these elementary row matrices look like. I skipped over that because I was concerned about getting through all the notes, but it helps to visualize the process. Okay. Now, as I mentioned earlier, it's not always possible to obtain the LU decomposition of a squared verbal matrix. So you talk about this is a uniqueness of LU. Okay. The first of six existence, it's not always the case. And here's a simple example of kind of matrix that does not have an LU decomposition. What if the 1, 1 entry is equal to 0? Because when you're working on the first column, all of your multipliers, mi1 is equal to ai1 divided by a11, which would not be undefined. So if you're carrying out Gaussian elimination on such a matrix, what you'd have to do is perform a row interchange. You'd have to swap the first row and some other row that has a non-zero entry in the first column, and then Gaussian elimination can proceed. But what that means is this particular A does not have an LU decomposition. But there are other kind of matrices where A11 is non-zero, but still not a LU decomposition. Actually, I'm going to whip up a simple example of that. Okay. So what you do is to work in the first column, you have M21 that eliminate the 2, 1 entry. That is equal to 2, and then eliminate the 3, 1 entry. So that's going to be 4 divided by 1. It's going to be 4. So what you're going to do is you're going to subtract twice the first row, the second row, and then 4 times the first row, the third row. So what you get is you have row 2 is equal to itself minus twice row 1. So 2 minus 2 is 0, 4 minus 2 is 0, and then 3 minus the minus 2 is going to give you 5. And then row 3 is equal to itself minus 4 times the first row. So we get 0 down here, and then -1, -8. And then 6 -4. Okay. So when our Gauss elimination algorithm proceeds to the second column, we have a 0 here. What?
We cannot make the -9 0.
Right. Yeah, so again, you'd have to interchange rows. Well, in fact, if we do interchange the second and third row, now we have an upper triangular matrix. So. Okay. Yeah. By the way, it drives me absolutely insane how many people misspell oops. They'll type out like OPPS. That's ops. Well, just like no one knows how to spell WOA anymore.
Anything.
Yeah,
Yes.
so our language is just gone. But, okay. When I was teaching at Stanford, I was teaching a C++ class. And at some point I got on a rant about this exact thing. And some student asked like, and how's this germane to programming? And it's like, tighten up. It's like, So, okay. I enjoyed teaching at USM over in Stanford. Stanford comes to teaching evaluations, they're mean. Okay. All right. So in general, when the VLU decomposition exists, so it actually is a general condition that can be stated. So if I define this matrix, I'll call it A sub k. Consists of the first k rows and columns. So it's a submatrix of A. So it's just taking the upper left k by k block. And this kind of matrix has a name. It's called a leading principal. That's number one, AL, not LE. Leading principal submatrix. Okay. All right. And then I could define the determinant of these leading principal submatrices. They're called principal minors. Okay, and I'll just call this MK for convenience. Okay, so now that I've established that terminology, the LU decomposition exists if and only if the principal minors are non-zero, all of them, k equal 1 to n. So we're already assuming that A as a whole is non-singular or invertible. So the A itself has a non-zero determinant for purposes of this discussion. But we need more than that. It's not enough that A as a whole is invertible. Each of these leading principal submatrices also has to be invertible. So here, this is M1 right here. So that's why we can't have that be 0. This example here, I contrived to make M2 equal to 0. So I intentionally set that part to be the matrix that is easily seen to be singular, and then I just made up entries for the rest. Any questions about the existence part? Okay. That's existence. What about uniqueness? So standard approach to any proof of uniqueness is you assume there are two and show that they must be equal. Let's assume a daily conflict with this, and that we have two of them, L1, U1, and L2, U2. Now, A is invertible, therefore both L's and both U's must be invertible. That's because determinant of product determinants. So we can work with the inverses of both of these. I'm just going to focus on this equation right here. And I'm going to multiply on the right by U1 inverse and multiply on the left by L2 inverse. So I'm going to get L2 inverse L1 on the left side, and on the right side, I'm going to have U2 U1 inverse. And this is where we use the properties of triangular matrices. Here we have unit lower times, well, L2 inverse is unit lower. So we're multiplying two unit lowers. The product is unit lower. So the left side of the equation is unit lower triangular. Here we have two upper triangulars. U1 is upper triangular, so its inverse is upper triangular. Now we have upper times upper. But that's what it amounts to. That because we have lower triangular equals upper triangular, so we can't have any non-zero entries away from a diagonal. So so both matrices must be diagonal. Because this says the upper triangle must be 0. This says the lower triangle must be 0. So both triangles are 0. Furthermore, because the left side is a unit lower triangular matrix, the diagonal entries are all 1. They must equal identity. But we have L2 inverse L1 equals identity. That means that L1 equals L2. And then similarly, U1 equals U2. So we have uniqueness. So we don't always have existence, but when we do have existence, we also have uniqueness.
Dr. Lambers.
Yeah.
Will this uniqueness extend when a permutation matrix is involved?
Okay, so so what will happen in that case? Yeah, actually, I'm just about to talk about pivoting. So in a case where LU doesn't exist for that particular A, you apply permutation matrix to A, and that matrix, a permuted matrix, will have an LU factorization, and that will be unique.
But if we used a different permutation, then we might end up with a different LU.
Yeah, because then what you have is a different matrix that you're
Excellent.
manufacturing. So yeah.
Thank you.
Yep. Okay. Questions about uniqueness? I don't know if I already said that. Okay. All right. So far, we've assumed that we've not had to perform row interchanges, but there are times when we do. So now I'm going to deal with that. And it's pivoting. Okay. Now, there are two very good reasons to perform row interchanges. First one is what I've just covered. That's if we have any final entry that's absolutely necessary to swap rows. But the thing is, here now, in an introductory linear algebra class, the discussion would end there. Like that you would only interchange rows if this condition comes up, and otherwise don't bother. But this is the numerical linear algebra world, where we do everything in floating point arithmetic. Even if the JJ entry was not 0, what if it was an incredibly small number? That could also cause problems. So the second reason for pivoting stems from issues regarding floating point arithmetic and the error that it incurs. We've examined the main step of Gaussian elimination. So that's where A I K is equal to itself minus the multiplier times the corresponding entry in row J. Because the thing is, as we go through this process, the entries of the original A might have some error in them, depending on how A itself was obtained. But even if it doesn't, the entries of A are modified by erroneous floating point arithmetic operations. So we're going to have some error in them. So here's the problem. If this multiplier Mij is large, then whatever error we have in this entry that's multiplying Ajk is amplified. So the error just keeps getting worse as you go through your columns from left to right. So the goal here, so our goal is we want the multipliers as small as possible. And actually, this is related to our first issue too. What if Ajj, again, was not 0, but a very small number? Well, Ajj goes in the denominator of a multiplier. So if that's incredibly small, the multiplier will be incredibly large, thus exacerbating this issue. So both issues 1 and 2 point to making the multiplier small. So how are we going to do that? I'll mention there are many approaches, but I'm just going to mention a couple of them that are frequently used. The most popular approach to pivoting. Partial pivoting. So in partial pivoting, you swap row J. When you're about to work on column J, swap row J of row P, where the magnitude of A Pj is equal to the maximum in absolute value of all the entries in column J on or below the diagonal. So the idea is you start at the diagonal and you take that part of a column from a diagonal to the bottom. You examine all the entries. You take the one that is the largest in absolute value and you place that entry on the diagonal. Because then it will follow after you perform the interchange. If you look at the multipliers, Aij over Ajj, if Ajj is guaranteed to be the largest of all of these entries, that guarantees that each multiplier is at most 1 in magnitude. So at least whatever error you're propagating, you're not making it worse, and maybe you're making it a little better. Now, we are adding operations, comparisons in this case, to Gauss elimination. What about the expense? And it still counts toward the overall effort. So the overhead of partial pivoting on the order of n squared comparisons. Because you're performing roughly n comparisons for a first column, n minus 1 for a second column, and so forth, but adds up to n squared. But Gauss elimination as a whole is order n cubed. So this expense of doing these comparisons is negligible, especially if the matrix is large. So not a big deal, and if it ensures that you have an LU decomposition, then of course it's worth it, and then also reducing the propagation of floating point error. So most implementations of Gauss elimination, for instance, like in MATLAB, will perform partial pivoting. Questions about that? The other popular approach is complete pivoting. So this takes us one step further. So you swap rows J and P and columns J and Q. So that's APQ is equal to the maximum. So in other words, you're searching the whole submatrix. So starting from row and column J, and you're searching all later rows, all later columns for the largest entry. and then you perform a row swap and a column swap to place that entry from that submatrix in the JJ position. Now, can anyone tell me what the overhead of this pivoting scheme would be? On the one hand, it will ensure multipliers that are even smaller than what partial pivoting would give. But
Less than and cheap though.
well, I mean, it's still order of n cubed. Because you're searching n squared entries, then n minus 1 squared, n minus 2 squared. So yeah, it may be like a constant times n cubed is less than 1. But in terms of but it's the number of comparisons is still a constant times n cubed. Which comes from sum of squares. From this formula. Yeah, so like roughly like 1/3 n cubed. Now, so that significantly impacts the expense of Gaussian elimination. But multipliers are even smaller, it contains a floating point error even better than partial pivoting would. But in the end, most people go partial pivoting because it's good enough from an accuracy standpoint and certainly is a lot more efficient. I will say though that the thing is, these days we take for granted that systems are solved using Gaussian elimination, general systems. If you have a system with a certain structure or sparse, then we can use iterative methods, and we'll talk about that later in the semester. But when electronic computers were first developed, so we first started using floating point arithmetic, there was concern that Gaussian elimination would be numerically unstable, that the error incurred would be too excessive. And there were some people back then who believed that. So then along came Jim Wilkinson, who performed a very careful round-off error analysis of Gaussian elimination. And when complete pivoting is used, it has been proven that it is numerically stable. I don't know offhand if it has been what has been proven in the case of partial pivoting, but it's been established that's good enough for in most cases. We'll talk later about when a matrix is ill-conditioned, and that's when you could have significant error in your solution. But once this was proved, then Gaussian elimination was accepted as a way for electronic computers to solve Ax equals B. And the thing is, you might wonder, like, well, what if it had been proven unstable? What would we even do? And iterative methods would have been the only other option. But they have trouble with all methods have trouble with ill-conditioned systems because conditioning is a property of a problem, not the method used to solve it. But yeah, it was a controversial thing back then. This has been well, I think Wilkinson probably did his work probably in the 60s or maybe late 50s.
We have.
Yeah, but it was back in those days, yeah. Okay. Yeah, and in the past, and I've actually presented that round of error analysis. It's pretty ugly. Because, before electronic computers, computer, the word computer referred to a person. It was a job title. You had people solving system linear equations, like from the Department of Agriculture. They'd sit at the desk all day and do everything by hand. And I guess they could use as many decimal places as they wanted. So, yeah, go figure. Yeah. Well, it's kind of weird how the electronic computers come along and tell your human computers that, you're all out of a job. So. Okay. Now, okay. So now that we have a pivoting scheme, how does it impact the overall solution process? All right. So the idea is, that's the form. You, if necessary, you swap row 1 with some row P. Now, where largest entry sits, so how the P is defined on the left of the board. Now, P might be equal to 1, in which case you don't swap anything. So what does that mean? You are multiplying A by what's called a permutation matrix. Actually, I'll use the same notation as in my notes. Okay, now, what is a permutation matrix? It's a matrix in which the rows or columns of the identity matrix are swapped, are rearranged according to what rearrangement you want to make. So you want to swap rows 2 and 3. Actually, 1 and 3. So the first row would be the third row of identity. Second row stays the same. Third row of permutation matrix is the first row of identity. So that would swap rows 1 and 3. So a permutation matrix has all entries equal to 0, except if it's n by n, there are n entries that are going to be equal to 1 that are arranged according to how you want to rearrange rows. If you multiply on the left, swap rows. If you multiply by permutation matrix on the right, it will swap columns. Now, a permutation matrix P is said to be orthogonal, meaning that P transpose times P is equal to identities. Another way of putting it is the inverse is equal to the transpose, which is very convenient. You don't have to do any work to compute the inverse. You just take the transpose. Orthogonal matrices are matrices that like they preserve length. Like if you are if you multiply a vector by an orthogonal matrix, it won't change the length. So it can be used to perform like a rigid motion, like a rotation or a reflection. Okay. So that's the first thing you do is you swap row one with some other row if you need to. And once that's done, you go ahead and eliminate whatever entries you need to in column one. So matrix A is overwritten with, so you have your permutation matrix, and then you have your elimination matrix that I mentioned before, the M1. Okay. So now column one is taken care of. Oh, dang, I'm about to run out of time. Wow, I just kind of flew away from me there. Okay. I mean, people finish everything, but. It's okay if I go 5 minutes, or does anybody have to? Okay. Then this process will repeat. So A multiplied by permutation matrix, elimination matrix, another permutation matrix that works on row 2, and so on. You keep going. And that is your U. So you figure out for row interchanges as you go. But the problem is we can't derive the LU factorization as we did before. Before, the L came from taking all the M's, inverting them and multiplying them, but now they're interlaced with these P's. But we actually can rearrange these. And I won't be able to go into all the details on them, but it is in the note. All right. So you have E times A equals LU. So it's like you're applying all the row interchanges up front, even though you're not actually doing that. You're figuring it out as you go. But we get P equals LU where L, well, first of all, P is equal to the product of all the permutation matrices you applied during the algorithm. So multiply in this order. So P1 gets applied first and P2 and so on. So it's almost like you could move all of the P's to the front of the line. But that cannot be done without affecting the M's. So L is equal to, as before, M1 inverse, M2 inverse, M minus 1 inverse, except they're going to put tildes on all of these M's. They are not the same as these M's here. They're just closely related. And I can write down the formula that MJ tilde is equal to the original MJ, but then you are multiplying on the left by all the permutation matrices to come on the left, and by their inverses or transposes on the right. So we actually do get an LU factorization of a row interchange version of A. All right, I have 2 more things to tell you and then I'll be done. So now the solution process. So you have this permuted LU factorization. And then you have AX equals B, and then you multiply both sides by P, then you get LUX is equal to PB. So whatever row interchanges you apply to A, you also got to apply to B. And UX is once again labeled as Y. So you solve LY is equal to PB by forward substitution. And then the last part is no different, UX equals Y by back substitution. That last but very important point I'll make. When you're coding up Gauss elimination with pivoting, partial pivoting, like you will do eventually in homework, you don't have to do all of this. So in terms of the implementation, it's actually simpler than what I described. Okay, because you're about to work on column J of A to eliminate entries. You figure out, oh, I gotta swap row J in some other row. So when you're swapping rows, you swap the entire rows. Because when you're working on A, you're eliminating entries and columns, then, okay, you're about to swap these rows, row J and row P, and everything in those rows to the left of column J is already 0 in the matrix A. But remember, those portions are not 0 anymore because what are you doing? You're storing multipliers in those portions. So when you swap these rows, you're swapping the portion of U that you're still working on, but you're also swapping the multipliers that you already had. That swapping of those multipliers accomplishes this for you. So easy peasy, lemon squeezy. One of our students said it all the time. I just had a reason to use it. So when you get to that homework problem, it's problem chapter 3, section 2, problem 20, Gauss elimination with partial pivoting. That's how you make sure you have the right factorization. Okay. And I made it to the end of the notes. So, yeah. It should be there.
Yeah, that's there.
Okay, and I don't mean just the quizzes, but homework one also? Okay, cool. All right. No, we don't have tests in this class. Yeah. Which is weird, because they have given a comprehensive exam before, but
Can I take one for this now?
I guess it's possible, but,
I'm already taking, I can't take 2 from the same sections.
oh, that's right, yeah.
I thought I could actually take this in something.
Okay, so sorry for running over time. I'm not surprised I still got to the end, even being 7 minutes late, but it will get better.